In this example, we are told that the rule of universal transitivity states that if we have these two universal conditional statements, for all x, p of x implies q of x, and for all x, q of x implies r of x, if these are both true, then we can conclude that for all x, p of x actually implies r of x. Okay, and so then this is true. That's what the rule tells us. And then I wrote here, provided the domains of the propositional functions are appropriate. Let's talk about that second here. Let's first justify the result independently, or using some other rules of logic that we've learned. And so let's think of a particular instance here, right? So let's just say x equals a. Let this be an instance that fits into this appropriate domain that we're not quite sure what that means yet. So then what this says then, right, and here let's make this even easier on ourselves, right, and let's write, say, p of a is equal to little p, q of a is equal to lowercase q, and r of a is equal to lowercase r. Right, so this is for a single particular instance of x in the domain, the proper domain. Now, let's see what happens, right? So this statement now says that P implies Q and Q implies R implies altogether, right? Implies altogether that P implies R. So notice here that the Q is behaving like a chain. In John Hammond's notes, he wrote that this rule is called the chain rule, or it's called the chain rule. Again, I said this in a previous lecture, but the chain rule has connotations back in calculus, so I like to use another name for it. And the other name for this rule is called syllogism. So this is the syllogism rule. And notice here, I said in that previous lecture that you could just call this transitivity because that's what's happening, right? You have P to Q, Q to R. You can skip over the whole deal and just go from P to R. And so this is called syllogism. And so that justifies the rule because this is true for every instance. We chose an instance, but we didn't say that it was any particular instance in our domain, right? We just said that it's an instance. All right, so what do we need to do about the domains conversation? So what's happening here? Well, we've got three different propositional functions, and their domains could theoretically all be different, right? So let's draw the domain. We'll call this the domain of the proposition P. And maybe the domain of the proposition Q overlaps it here. And finally, we'll have the domain of our third propositional function R. Domain of R. And what we want to show, or what we want to conclude, right, is that, if we scroll back up, we want to conclude that if we can go P of x implies Q of x, and then Q of x in turn implies R of x, that we can just go straight from P of x to R of x, right, in a logical sense. But for that to happen, then x has to be in the common domain of all three of these, right? So whatever our domain is, if it's possible that the domains don't have areas where they don't overlap, right? So P implies Q. For example, let's just look at this picture. P implies Q. Let me get my highlighter. P implies Q is defined on the intersection of the domains of P and Q. Right? So P implies Q is defined on here. P implies P implies R, which is the the end result, would be defined theoretically over here, right? And then finally we have Q implies R, which is really the intermediate step, is defined on this domain right here, this intersection. And what's common to all of these is that they all have to be contained here. So if you want to go from one to the next and you want to string this together and get to R by going through Q, then you have to use the domain which is the common intersection. So it's like the triple intersection here. And now if you really want this to be well defined, you just have to ensure that the domains of these things coincide, right? So the domains must coincide. Whatever the domains are, they must coincide. So the domains either must coincide, or the other option is that the statement up here doesn't actually apply to all x, it just applies to the all x in this common intersection, right? So, or this universal statement applies to the domain, which will have to, in other words, you have to redefine the domain, which would be the intersections of the domain of P intersected with the domain of Q intersected with the domain of R. Okay. All right. So hopefully this makes sense. But the idea is that P implies Q up here, right? But that does not imply you cannot go then from Q to R because it's not any overlap over here. So um, a little bit subtle, but the idea is that either they coincide, that would be the best case situation, right? Or you have to redefine what you mean by the universal quantifier, or change the domain when you try to use the universal quantifier and change it to the common intersection of all three of these sets.